To calculate the actual power of a motor when increasing the frequency, understand that increasing the frequency or torque will indeed increase the current. The core formula to determine the actual power of the motor based on the feed frequency is expressed as power in watts equals torque in Newton meters multiplied by angular speed in radians per second. The angular speed in radians per second is calculated as 2 multiplied by pi multiplied by the frequency in hertz, then divided by 60. Therefore, the complete formula becomes power in watts equals torque in Newton meters multiplied by 2 multiplied by pi multiplied by the frequency in hertz, then divided by 60. Let's apply this to a practical scenario. Consider a 20 horsepower motor, which is approximately equivalent to 14.9 kilowatts. If this motor is driven at 100 Hz, the angular speed can be calculated as follows. Angular speed equals 2 multiplied by pi multiplied by 100 Hz, then divided by 60, resulting in approximately 104.72 radians per second. Now substitute these values into the power formula. Power in watts equals 14.9 kilowatts multiplied by 104.72 radians per second, which equals approximately 1.56 megawatts. This calculation suggests that the actual power of the motor is approximately 1.56 megawatts when driven at 100 Hz. However, it is important to remember that this formula offers an approximation. The actual power may vary slightly depending on the motor's efficiency and other operational factors. There are additional considerations to keep in mind. Firstly, the duty cycle of the motor is very short, with a maximum of 10% and a normal operation around 3%. This implies that the motor is not consistently running at its full power capacity. Secondly, it is crucial to consider the thermal capacity of the motor. Operating the motor at an elevated frequency can lead to increased temperatures. Ensure the motor has adequate cooling mechanisms to prevent overheating and potential damage. To elaborate further, the relationship between frequency and motor performance is not linear and involves several complex factors. When a variable frequency drive, or VFD, is used to increase the frequency supplied to the motor, it effectively increases the motor's speed beyond its nameplate rating. This is often done to achieve higher output speed or to increase the motor's power output for short durations. However, this approach has implications that must be carefully managed. When the frequency is increased, the motor's back electromotive force, or back EMF, also increases. The VFD compensates for this by increasing the applied voltage to maintain a constant volts per hertz ratio. This ratio is critical for maintaining the motor's magnetic flux at the appropriate level. If the voltage does not increase proportionally with the frequency, the motor may experience reduced torque capability and increased current draw, leading to inefficiencies and potential overheating. The torque produced by an induction motor is directly proportional to the square of the applied voltage and inversely proportional to the synchronous speed. However, beyond the base frequency, the voltage cannot be increased further due to the VFD voltage limit, which is typically equal to the mains voltage. Consequently, when the frequency exceeds the base frequency, the motor operates in a constant power region where the torque decreases linearly with the increase in frequency. This relationship is vital to understand because it directly affects the motor's ability to handle loads at higher speeds. In the context of the provided scenario, where the motor operates at 100 Hz, twice its rated frequency of 50 Hz, the motor is likely operating well into the constant power region. The torque available at 100 Hz will be significantly lower than the torque available at 50 Hz, which is a crucial factor to consider in the application's design. Another important consideration is the motor's cooling capacity. Motors are typically cooled by an internal fan that is directly coupled to the motor shaft. The effectiveness of this cooling system is directly proportional to the motor's speed. When the motor operates at higher frequencies, the fan spins faster, providing more effective cooling. However, this is only true up to a certain point. At very high speeds, the fan's efficiency may decrease, and the increased heat generated by the motor due to higher frequency operation may exceed the cooling system's capacity. Therefore, it is essential to monitor the motor's temperature and ensure that it remains within the manufacturer's specified limits. If the motor's temperature exceeds these limits, it may be necessary to lower the motor's output power or provide additional cooling measures, such as an external cooling fan. The motor's duty cycle also plays a significant role in its thermal management. A short duty cycle, such as the 10% maximum and 3% normal specified in the scenario, means that the motor is only operating under load for a small fraction of the time. This allows the motor to cool down during the off periods, which can significantly reduce the risk of overheating. However, even with a short duty cycle, it is still essential to consider the motor's thermal capacity and ensure that it is not being overloaded. The thermal capacity of a motor refers to its ability to absorb and dissipate heat. Motors with higher thermal capacity can withstand higher temperatures for longer periods without experiencing damage. When selecting a motor for a specific application, it is crucial to consider its thermal capacity and ensure that it is appropriate for the expected operating conditions. In addition to these factors, it is also essential to consider the motor's insulation class. The insulation class specifies the maximum temperature that the motor's insulation can withstand without breaking down. Operating a motor beyond its insulation class temperature can lead to premature failure. Therefore, it is crucial to ensure that the motor's operating temperature remains within the limits specified by its insulation class. To accurately calculate the actual power of the motor, it is essential to have accurate data on the motor's torque, speed, and efficiency. The motor's nameplate provides some of this information, but it may not be sufficient for precise calculations. It may be necessary to perform additional testing to determine the motor's actual performance characteristics under the specific operating conditions. Furthermore, the formula provided earlier is a simplified representation of the motor's power calculation. In reality, the motor's power output is also affected by factors such as the motor's slip, which is the difference between the synchronous speed and the rotor speed, and the motor's power factor, which is the ratio of real power to apparent power. These factors can be difficult to measure accurately, but they can have a significant impact on the motor's actual power output. Therefore, it is essential to consider these factors when performing motor power calculations. In summary, increasing the frequency of a motor can increase its power output, but it also introduces several challenges that must be carefully managed. These challenges include maintaining the appropriate volts per Hertz ratio, managing the motor's thermal capacity, and ensuring that the motor's operating temperature remains within its specified limits. By carefully considering these factors, it is possible to safely and effectively operate a motor at higher frequencies and achieve the desired performance characteristics. Moreover, the type of load connected to the motor influences the power calculation. Constant torque loads, such as conveyors or positive displacement pumps, require the motor to maintain a consistent torque output regardless of speed. In contrast, variable torque loads, such as centrifugal pumps or fans, have a torque requirement that increases with the square of the speed. Understanding the load type is crucial for accurately determining the motor's power requirements at different frequencies. For constant torque loads, the power required increases linearly with the frequency. This means that if the frequency is doubled, the power required also doubles. However, for variable torque loads, the power required increases with the cube of the frequency. This means that if the frequency is doubled, the power required increases by a factor of 8. Therefore, it is essential to consider the load type when calculating the motor's power requirements, especially at higher frequencies. Additionally, the motor's efficiency varies with the load and speed. Motors are typically most efficient when operating near their rated load and speed. As the load and speed deviate from the rated values, the motor's efficiency decreases. This means that the actual power consumed by the motor may be higher than the calculated power output, especially at higher frequencies and lower loads. Therefore, it is essential to consider the motor's efficiency when calculating the actual power consumption. To accurately determine the motor's efficiency, it is necessary to consult the motor's performance curves, which are typically provided by the manufacturer. These curves show the motor's efficiency at different loads and speeds. By using these curves, it is possible to estimate the motor's actual power consumption more accurately. Furthermore, the power quality of the electrical supply can also affect the motor's performance. Poor power quality, such as voltage sags, voltage swells, or harmonic distortion, can lead to increased motor losses and reduced efficiency. Therefore, it is essential to ensure that the electrical supply to the motor is of good quality. Voltage sags and swells can cause the motor to draw more current, leading to increased heating and reduced lifespan. Harmonic distortion can also cause increased heating and can interfere with the operation of the VFD. To mitigate the effects of poor power quality, it may be necessary to install power conditioning equipment such as surge suppressors, harmonic filters, or voltage regulators. These devices can help to improve the power quality and protect the motor from damage. In addition to these considerations, it is also important to properly size the VFD for the motor. The VFD should be rated to handle the motor's full load current and voltage. If the VFD is undersized, it may overheat and fail. Furthermore, the VFD should be properly configured for the motor's specific characteristics such as its voltage, current, and speed. Improper VFD configuration can lead to reduced motor performance and increased energy consumption. To ensure proper VFD sizing and configuration, it is essential to consult the VFD manufacturer's recommendations and follow their instructions carefully. Finally, regular maintenance is crucial for ensuring the long-term reliability of the motor and VFD. This includes inspecting the motor and VFD for signs of wear and tear, lubricating the motor bearings, and cleaning the motor and VFD to remove dirt and debris. Proper maintenance can help to prevent premature failure and extend the lifespan of the motor and VFD. In conclusion, calculating the actual power of a motor at increased frequencies requires careful consideration of several factors, including the motor's torque, speed, efficiency, load type, power quality, and VFD configuration. By addressing these factors, it is possible to safely and effectively operate a motor at higher frequencies and achieve the desired performance characteristics. Additionally, it is important to continuously monitor the motor's performance and make adjustments as needed to optimize its efficiency and reliability. Regular maintenance and proper VFD configuration are also essential for ensuring the long-term success of the application. By following these guidelines, it is possible to maximize the benefits of operating a motor at increased frequencies while minimizing the risks. Remember to always consult with qualified professionals for specific applications and adhere to all relevant safety standards and regulations.